This chapter moves from the goal of prediction to overfitting, cross-validation, regularisation, and regression trees. We then compare models on the apartment data, discuss selection criteria, and finish with practical guidance and a compact summary. By the end, you should be able to explain the bias-variance trade-off, evaluate a model on unseen data, fit ridge and lasso models, choose the penalty by cross-validation, and carry out the workflow in both R and Python. So far, we have often cared about interpreting coefficients. Prediction asks a different question. How accurately can we forecast an outcome we have not yet observed? A hospital may forecast emergency room arrivals, a broker may forecast an apartment price, and a city planner may forecast an air pollution peak. In this setting, a useful model is one that predicts well. A coefficient need not have a causal interpretation, and a predictor need not be easy to interpret. Keep the three goals separate. Description summarizes what the data look like, using statistics, figures, and measures such as R². Prediction asks how well we can forecast the outcome, so test error and cross-validation matter. Causal analysis asks what would happen to the outcome if a treatment changed, which requires a credible design. This chapter is about the middle goal. Good predictive performance alone does not turn a coefficient into a causal effect. Let the outcome be continuous, and let the model use several covariates to produce a predicted value. Our population target is mean squared prediction error, the expected squared gap between the outcome and its prediction. The best prediction function is therefore the conditional mean of the outcome given the covariates. In the training sample, we calculate the analogous mean squared error, but that ensample number is not yet an honest measure of future performance. Least squares minimizes the residual sum of squares, so adding another term can never raise the training mean squared error. A higher order polynomial will always fit the observations at least as well as a lower order one. That mathematical fact creates a statistical danger. The extra flexibility may follow accidental features of this sample rather than stable structure in the population. Overfitting means fitting the training data extremely well while predicting new observations poorly. The apartment example shows the trap. As the polynomial degree rises from a straight line to a very flexible curve, the training error falls monotonically. The most elaborate model therefore looks best if we judge it only on the observations used to estimate it. Yet the degree 15 curve produces implausible forecasts for large apartments. A smaller training error is guaranteed by added flexibility. Better out-of-sample prediction is not. The decomposition explains why prediction error does not fall forever. One part is squared bias, the gap between the true conditional mean and the average prediction made by the procedure. A second part is estimator variance, how much the fitted prediction changes across possible training samples. The third is genuine outcome uncertainty, which no model can remove. Model choice can trade bias against variance, but it cannot eliminate the irreducible noise in the outcome. A simple model may miss important curvature, creating bias, but it is relatively stable across samples. A complex model can reduce bias while becoming much more sensitive to which observations happen to be sampled. Genuine uncertainty stays fixed, so the model selection problem is to balance only the first two terms. This is why neither the most rigid model nor the most flexible model is automatically best. We want the point where their combined contribution to prediction error is smallest. The bias-variance trade-off changes with sample size. More complex models usually lower bias and raise variance. Simpler models do the reverse. With more observations, coefficient estimates become more stable, so we can afford greater flexibility. In the simulation described here, a linear model wins with the smallest sample, a quadratic wins with a larger sample, and a cubic wins with the largest. Complexity is therefore not an intrinsic virtue or flaw. It must be judged relative to the information available. The diagram gives the visual summary. Squared bias falls as complexity increases while variance rises. Their sum, the mean squared error apart from genuine uncertainty, forms a U-shaped curve. The best model sits near the bottom, not at either extreme. Notice that this optimum is about expected performance on new data. Training error alone would keep moving downward and would push us too far to the right into the high variance region. An honest evaluation begins by separating the observations. The training data estimate the model. The test data are held back to evaluate predictive performance. Because the test observations played no role in fitting, their mean squared error is a better estimate of future error than the training error. A common split is roughly 4/5 for training and 1/5 for testing, although the precise division depends on sample size and the role of validation. Now compare the apartment models on the two samples. Training error keeps falling as the polynomial becomes more flexible, but test error reaches its minimum with the quadratic model and then rises. The degree 10 model has the best training fit and the worst test performance among the three shown. That reversal is the signature of overfitting. Train on the training data, choose using validation or cross-validation, and reserve the test data for a final, honest assessment. A single training test split is not enough when we compare many specifications. The winning model may simply be the one that got lucky on that particular test sample, and the smallest observed test error is then biased downward. The remedy is a three-way discipline. Fit candidates on training data, select among them using validation data, and use the test sample only once at the end. Cross-validation provides a more data-efficient version of the validation step. In fold cross-validation, divide the data into several roughly equal parts. Hold out one fold, fit the model on all remaining folds, and calculate prediction error on the held-out observations. Repeat until every fold has served as validation once, then average the fold errors. Each observation is evaluated by a model that did not train on it. The resulting average is therefore an out-of-sample estimate that uses the available data efficiently. 5 or 10 folds are common because they balance computation, bias, and variability. Leave one out. Cross-validation takes the number of folds all the way to the sample size, so each model trains on nearly every observation. It has low bias but can be computationally expensive and surprisingly variable. With modern software, 10-fold cross-validation is often a sensible default. The purpose is not ritual, it is to compare candidate models on the same out-of-sample basis. The R code begins the workflow by reading the apartment data and fixing the random seed. It samples roughly 80% of the row indices for training and assigns the remainder to the test set. The important object is not the punctuation, but the separation. The test rows are set aside before any model choice. Reproducibility matters here because another random split can produce a different comparison, especially in a modest sample. Next, fit the least squares model on the training frame only. Predict once for the training observations and once for the untouched test observations, then average the squared residuals in each group. The test error should usually exceed the training error because the model was optimized on the latter. If the gap is large, suspect overfitting. The code also makes a useful audit trail. The same fitted object generates both sets of predictions, so the only difference is the data supplied. For cross-validation in R, this page creates 5-fold labels after fixing the seed. Every row receives exactly one label, and an empty vector is prepared to store one validation error per fold. Notice that the folds are defined before the loop begins. We want every candidate specification to face the same partitions, otherwise differences in estimated performance would partly reflect different random splits rather than the models themselves. The loop implements the algorithm directly. For each fold, the code trains on rows outside that fold, predicts for the held-out rows, and stores their mean squared error. Averaging the stored values produces the cross-validated estimate. The line excluding the current fold is the crucial safeguard against leakage. Once this structure is correct, we can place different formulas inside the loop and compare their cross-validated errors on equal terms. The Python setup uses the same logic. After loading the apartment data, it defines the predictor matrix and outcome vector, then constructs a shuffled five-fold splitter with a fixed random state. Shuffling is appropriate here because the observations are not ordered in time. The splitter records which rows will train and validate in each round. A later page will loop over those indices, so the statistical design is visible before any estimator is fitted. The Python loop receives training and validation indices from the splitter. It fits a linear model only on the training rows, predicts the held-out outcomes, records the mean squared error, and finally averages across folds. The software offers a one-line cross-validation score as well, but this explicit loop is pedagogically valuable. It shows exactly where the separation occurs. Whenever you build a more complex pipeline, every data-dependent step must also be fitted inside that training portion. With many potential predictors, manual specification search quickly becomes impossible. The example combines continuous variables, categorical indicators, polynomial terms, and pairwise interactions to create more than 150 candidate variables. That already implies more possible subsets than we could enumerate. The solution is not to try every subset. We need methods that control complexity automatically, using a penalty and out-of-sample performance to decide how much flexibility the data can support. Regularisation modifies the least squares objective by penalising large slope coefficients. Ridge uses the sum of squared slopes. Lasso uses the sum of absolute slopes. Both deliberately introduce some bias because the estimates are pulled towards zero, but they can reduce variance enough to improve prediction. This is the same bias-variance trade-off in a new form. The intercept is normally left unpenalized, and the amount of shrinkage will be chosen from the data. Ridge regression minimizes the residual sum of squares plus lambda times the sum of squared slopes. If lambda is zero, we recover ordinary least squares. As lambda grows, every slope is pulled more strongly towards zero. In the limiting case, they approach zero, although ridge does not normally set them exactly to zero. Lambda is therefore a complexity control. A small value allows a flexible fit, while a large value favors a stable, heavily shrunken model. Ridge retains every predictor, reduces variance, and is particularly useful when many variables each carry a small signal, but the penalty depends on coefficient scale. A variable measured in large units may have a small coefficient simply because of its units and would otherwise receive a different effective penalty. Standardizing continuous predictors to mean zero and standard deviation, one makes the shrinkage comparable across variables. We do not choose lambda by looking at training fit, which would always favor no penalty. Instead, repeat cross-validation for a grid of candidate values. Within each fold, fit ridge on the remaining data and evaluate the held-out error, average the errors for each lambda, and select the minimizer. The selected value is an empirical compromise between fit and stability. In R, the cross-validated fitting function automates this entire comparison while preserving the same logic. Lasso changes only the shape of the penalty. It uses absolute coefficient values rather than squares. That apparently small change has a major consequence. Some fitted slopes become exactly zero, so Lasso performs variable selection while shrinking the retained coefficients. This is attractive when the true signal is sparse. Like ridge, it must be tuned by cross-validation, and its coefficients should not be interpreted causally simply because the procedure selected them. The comparison table highlights the practical choice. Ridge keeps all variables and works well when many predictors have small effects, especially when they are correlated. Lasso can drop variables entirely and is better suited to a sparse signal in which only a few predictors matter. Both tune lambda by cross-validation. The choice is ultimately predictive, not philosophical. Compare their validation errors and remember that the representation of the predictors can matter as much as the penalty itself. ElasticNet blends the two penalties. Alpha controls the mixture. 1 gives pure Lasso, 0 gives pure ridge, and intermediate values combine variable selection with ridge-like handling of correlated predictors. Lambda still controls the overall strength. Both tuning parameters should be selected using cross-validation. ElasticNet is often a useful compromise when we expect sparsity, but several predictors measure closely related features, so Lasso might otherwise choose one rather arbitrarily. This page makes the scaling issue explicit. Measuring income monthly rather than annually changes the coefficient and therefore changes the penalty, even though the underlying information is identical. Standardize continuous predictors before fitting. Binary indicators are usually left on their original 0-1 scale. The displayed R package standardizes predictors by default. The R implementation uses a model matrix to expand categorical variables and create the numerical design matrix required by the regularisation package. Cross-validated ridge uses a mixing parameter of 0, while Lasso uses 1. Each fitted object stores its selected lambda, and the final two lines report those values. The page therefore records both fitted models and the data-driven complexity chosen for each penalty. The Python preparation removes incomplete rows, separates the outcome, and creates indicator columns for the categorical predictors. It then converts the resulting frame into the numerical matrix expected by the estimators. This page is where silent sample changes can occur, so check the number of retained observations. The continuous scaling will be handled later inside a pipeline, which is safer than standardizing the full matrix before cross-validation. The Python models place the standardization step and the penalized estimator in a single pipeline. Ridge and Lasso each search over a grid of penalty values using 5-fold cross-validation. Keeping the scaler inside the pipeline is essential. In each fold, its mean and standard deviation are learned only from the training rows. The validation rows are transformed using those training estimates. That small design choice prevents information leakage and makes the reported error genuinely out of sample. A regression tree predicts by dividing the covariate space into regions and using the mean outcome within each region. The algorithm searches for the variable and split point that most reduce residual variation, then repeats within the new regions. This naturally captures non-linearity and interactions without writing them into a formula. The book develops classification and regression trees and pruning in detail. Ensembles such as random forests and boosting build on the same basic idea. Regression trees handle non-linearity and interactions automatically, require no pre-specified functional form, and are easy to visualize. Their weakness is instability. Small changes in the training sample can change the early splits and the whole tree. That instability motivates pruning and ensemble methods in applied work. An unpruned tree can overfit. Cost complexity pruning adds a penalty proportional to the number of terminal nodes. With alpha equal to 0, the full tree is retained. As alpha increases, the selected tree becomes smaller. Choose alpha by cross-validation. In R, the R part package uses the CP parameter for this penalty. The model comparison returns to the apartment data. 7 predictors include size, rooms, construction status, monthly fee, build year, elevator, and metropolitan area. The same training test split is used throughout. Complexity enters through the treatment of build year. One specification gives every year its own indicator, while another pools years into decades. This setup lets us see that feature design can matter as much as choosing among ordinary least squares, ridge, lasso, and trees. Read the test column, not only the training column. Ordinary least squares with year indicators has the smallest training error but a much larger test error. Lasso with decade indicators gives the best test error, just under 1.2, while the single tree performs poorly. The pattern is a concrete bias-variance lesson. A flexible representation can fit the training sample beautifully and still generalize worse than a coarser, slightly biased specification. Several lessons follow. Year-by-year indicators produce classic overfitting, lowest training error, highest test error. Lasso with decade indicators performs best on the held-out sample. More generally, the simpler decade representation beats the apparently richer annual representation, and the tree gains little here because the strongest relationships do not require many threshold interactions. The main conclusion is methodological. Model selection cannot be based on training performance alone. Why does pooling years into decades help? An apartment built in 1964 should not receive a wholly unrelated effect from one built in 1965. Separate annual indicators estimate many noisy parameters and create high variance. Decade indicators pool neighbouring years, accepting a little bias in exchange for much greater stability. In this application, that trade improves test performance. The right level of granularity matters more than whether the final estimator is ordinary least squares, ridge, or lasso. Cross-validation is not the only way to compare models. The Akeke and Bayesian information criteria reward fit through the residual sum of squares and penalize the number of parameters. The Bayesian criterion imposes the stronger penalty once the sample is moderately large. Lower values are preferred. These criteria are convenient when no separate test sample is available, but they remain in-sample approximations. Cross-validation estimates predictive performance more directly and need not choose the same model. Adjusted R-squared also penalizes extra parameters. Unlike ordinary R-squared, it can fall when a newly added variable fails to improve fit enough, but keep the distinction on the page in mind. Adjusted R-squared and the information criteria evaluate in-sample fit with a complexity correction. Cross-validation directly estimates out-of-sample error. They often agree, but there is no guarantee. For a prediction task, held-out performance should normally carry the greatest weight. Use ridge when many predictors plausibly carry small non-zero signals and when correlations among them are substantial. Use lasso when only a few predictors are likely to matter and automatic variable selection is valuable. Elastic net combines the two strengths. These are starting expectations, not rules that replace evidence. In practice, fit all three with the same folds and compare validation error. A method that sounds appropriate can still lose once the actual signal and sample size are taken into account. Trees are especially attractive when interactions are numerous, the relationship is strongly nonlinear, or we want the algorithm to choose thresholds and variables automatically. A single tree is interpretable, but unstable. Random forests and gradient boosting sacrifice some simplicity to improve prediction, and they often outperform an individual tree. Even then, tune them on validation data and evaluate only once on the test data. Flexible algorithms do not remove the need for an honest design. A practical prediction project follows a sequence. Define the outcome and plausible predictors, address missing values, decide which transformations and interactions are candidates, then split the data into training, validation, and test portions. Fit competing models only on training data, select using validation or cross-validation, and report the final test error once. Finish by plotting residuals or prediction errors to look for systematic underprediction, overprediction, or subgroups where performance breaks down. A low test error establishes predictive value, not causation. A lasso model might discard build year and retain elevator because that combination forecasts apartment prices well. It does not tell us the effect of installing an elevator because the selected predictors may proxy for many other features. Causal claims require a design such as random assignment, instrumental variables, difference in differences, or regression discontinuity. Different questions require different evidence, even when they use the same outcome and covariates. Information leakage occurs when test or future information slips into training. Standardizing with the full sample, choosing principal components on all observations, randomly splitting adjacent dates from a time panel, or tuning hyperparameters against the test error can all make performance look better than it will be in practice. The common thread is that the model has learned something it would not know at prediction time. Leakage produces optimistic error estimates even when every line of code runs correctly. Prevent leakage by fitting every data-dependent preprocessing step inside the training fold. Learn the scalar, imputer, or principal components from training rows, then apply that fitted transformation to validation or test rows. Pipelines in Python and comparable workflows in R enforce this separation. The reason is statistical, not merely computational. If validation information shapes the transformation, the resulting error no longer estimates performance on genuinely new data. A random forest grows many trees on bootstrap samples and considers only a random subset of predictors at each split. Bootstrap sampling exposes the trees to different rows. Feature sampling prevents the same strong variable from dominating every tree. Averaging their predictions greatly reduces the variance of a single tree while keeping bias relatively low. The individual trees may overfit, but their errors are imperfectly correlated, so the ensemble can generalize well. The main tuning choices are the number of trees, the number of candidate features considered at each split, and tree depth. More trees stabilize the average but increase computation. Feature sampling controls diversity. Depth controls complexity. Both languages provide standard random forest implementations. These defaults are useful starting points, not guarantees. Tune the influential parameters with cross-validation and report performance on a final test set that remained untouched throughout the search. Ordinary shuffled cross-validation is invalid for time series because it can train on future observations and validate on the past. Rolling window validation respects temporal order. Fit on the earliest observations, predict the next period, expand the training window, and repeat. Averaging these sequential errors estimates how the procedure would have forecast in real time. The principle is simple. The validation design must reproduce the information that would actually have been available at each prediction date. A rolling design can use an expanding window, retaining all past observations, or a fixed window, dropping the oldest as new data arrive. Expanding windows use more information, but may average over obsolete patterns. Fixed windows keep a more stable recent regime, but sacrifice sample size. The right choice depends on how quickly the data generating process changes. Both R and Python include time series splitters, but we still need to decide which historical information is substantively relevant. Gradient boosting builds trees sequentially rather than independently. Each new tree is fitted to the remaining error, or more generally to the negative gradient of the loss function, and its contribution is scaled by a learning rate. The ensemble gradually corrects mistakes made by earlier trees. Small learning rates usually require more trees, but can improve generalization. Because the trees depend on one another, boosting is powerful but sensitive to depth, learning rate, and the number of stages. Random forests and gradient boosting solve different ensemble problems. A random forest grows trees in parallel and averages them, mainly reducing variance. Boosting grows trees sequentially, with later trees correcting residual errors and can reduce bias. Popular implementations make both accessible, but neither is automatically superior. Compare them with the same validation design and tune depth, the number of trees, and the learning rate without looking at the final test outcomes. The central ideas now fit together. Overfitting means excellent training fit and poor future prediction. Complexity lowers bias but can raise variance. Cross-validation estimates out-of-sample error. Ridge shrinks all slopes. Lasso can set some exactly to 0. Lambda is selected by validation. Trees partition the covariate space without assuming a linear form. Across all these methods, the criterion is the same: performance on observations that did not help fit or tune the model. This formula page is a compact map. Training mean squared error averages fitted residuals and is optimistically low. Cross-validated error averages the validation errors across folds. Ridge adds a squared coefficient penalty, Lasso an absolute value penalty, and elastic net mixes the two through alpha. Do not read the symbols as separate facts. Each formula changes how complexity is assessed or controlled, and each tuning decision must be made without using the final test sample. The software summary pairs the methods across languages. In R, the regularisation package fits Ridge and Lasso, and its cross-validation function selects Lambda. The tree package fits and prunes regression trees. In Python, the linear model module provides cross-validated Ridge and Lasso. The model selection module provides fold splitting, and the tree module provides regression trees. The syntax differs, but the required workflow is identical: pre-process within folds, tune on validation data, and evaluate once on held-out observations. Use these questions to test the logic. Ask how sample size affects complexity, when Lasso should beat Ridge, why training and test error disagree, whether prediction supports causation, and why the test data must remain untouched until the end.